Okay, students, so we are into our fifth lecture, the second week. We have been talking about Gibbs phase rule and a few other things. We took the L2SiO5 diagram and saw the ramifications of the diagram, what this diagram would evolve into if you made the system a little more complex. But we took very simple minerals to start with. So in this lecture, I would try to find out the Gibbs phase rule and etc. for a somewhat larger system and introduce you to the complications that are induced by fluids. And it's not very easy, but I will start a little bit with the fluids first, and then we go into the assemblage. I don't know whether I will be able to go further. I want to do this slowly so that you can get the full hang of it before we go into further complications. Right. We all know this equation, this reaction. Muscovite, you must have written it somewhere or the other. Now, this is an equation which you must be familiar with. This term might be unfamiliar. It's not a mineral, it's called aluminosilicates, AS. So it could be sillimanite, andalusite, or kyanite. And so it's time possibly to start writing equations a little bit, reactions a little bit. And say, for example, the formula for muscovite is K, the idealized formula is KAl2 Al Si3 O10 OH twice. Quartz is Si. SiO2. K-feldspar, this has several polymorphs. I don't know whether you know. Say, for example, the high temperature form is called sanidine, S-A-N-I-D-I-N-E. Then you have orthoclase, which you might be familiar with. Then you have microcline, M-I-C-R-O-C-L-I-N-E, and adularia, A-D-U-L-A-R-I-A. And this is some sort of a temperature variation. Sanidine, orthoclase, microcline, adularia. Progressively lower temperature polymorphs, broadly speaking. K-feldspar, and this is formula is KAlSi3O8. Aluminosilicate, Al2SiO5. You can see here I'm taking very generalized formulas, very simple formulas, not going into any sort of complication. And the fluid is H2O. Fluid is H2O. These are phases and these are formulas, meaning phase components. All of them are taken to be pure. All of them are taken to be pure. And that is why I have written only one end member component. I have not put in any variations in this. But you know, K-feldspar is a solid solution between NaAlSi3O8 and albite, which is NaAlSi3O8. But I have not considered that. We will come to that later on. Quartz we have taken pure. Muscovite, there's an N-member composition of muscovite, classical composition of muscovite. I have not added celadonite component to it. So you know, if you add celadonite component, your mica becomes sphengitic. So I have avoided all complications. Aluminosilicate Al2SiO5 and fluid, we say, is pure H2O. Now the reaction, if you write, it is like this: KAl2, AlSi3, O10 OH whole twice. These are the reactants. Plus SiO2 is equal to KAlSi3O8 plus Al2SiO5 plus H2O. This is the famous reaction by which muscovite, this is the low temperature side, this part is low temperature part, and this is the high temperature part. Now, if I draw a diagram, temperature, pressure, and this is how the reaction looks like, with muscovite and quartz to the left, low temperature, and K-feldspar aluminosilicate H2O. H2O, of course, you can't see, so K-feldspar aluminosilicate is the high temperature form. I will introduce you to a small term which you read in class 12. It is called the Clausius-Clapeyron equation. The formula is dt by dp, or dp by dt is equal to del SR by del VR. This is the equation. dp by dt is equal to del SR by del VR. We will talk about this equation a little later. This is the entropy change of the reaction. That means entropy of the products minus the entropy of the reactants. This is delta VR. It's called the volume change of the reaction, which is volume of the product minus the volume of the reactants. This is delta is always product minus reactant. R subscript means a reaction. So you see here, if this is the nature of the curve, then if I draw a tangent at this point, and if I draw a tangent at this point, so you can see here, dp by dt tends to infinity. Whereas if I take it here, dp by dt tends to 0. It becomes flat like this. It's not 0, but tends to 0. This is not infinity, tends to infinity. This is dp, change in pressure as a function of temperature. Change in pressure as a function of temperature, you can see large pressure difference, small temperature, large value of P, very small value of T, so it's infinity. And this is just the reverse, large value, small value of P and a large value of dP. It is the same as This is dP and this is dt. Right? Okay. So what we see here in this reaction, the slope of the reaction, that means the dP by dt of the reaction tends to zero at low pressure temperature, and dP by dt tends to infinity at high pressure, high temperature. Now, if dP by dt tends to zero, that means delta VR should be very large, yes or no, compared to delta SR. Have you understood? dP by dt, if this is equal to 0 or tends to 0, that means the denominator, which is the delta VR, should be very big compared to del SR, or del SR should be close to 0. Normally, and in this part, dP by dP is very large. How can you have this large? If delta VR is small. Have you understood? So why this change of graph? Is because of a very simple reason. Because of this gentleman called H2O. At very high pressure, H2O, you know, is a fluid, is a highly compressible thing. So if you increase pressure, the volume of H2O, the molar volume of H2O decreases dramatically. But if your pressure is very low, then the delta VR is large. Do you understand? So in this type of a reaction, normally, since delta VR is very large, because the highly compressible delta VR is very large at low pressure, so the reaction slopes are gentle. Whereas at higher pressure, delta VR is much large, the pressure is much large, and this dramatically decreases the delta VR of this place. That is why many of these reactions, or most of this reaction, have this type of a slope. The change in slope is because of the compressibility, fluid compressibility as a function of pressure. At high pressure, it has a small volume. At low pressure, it has a large volume, and hence the change of dP by dt. This is just for your information. Now, where am I keeping this? Here. I will draw this diagram again. Now, all these phases, muscovite quartz, K-feldspar aluminosilicate, these are all pure phases. Let us say the fluid. I think what I will do here, I will write fluid and then write H2O in it. Okay, so here fluid is the phase. We will talk about it in greater detail later on. Fluid is and composed of H2O. Right? If we take the fluid also as pure H2O, then for a pure fluid, XH2O equal to 1. There is no doubt about it. So what we write here is 1. This value is XH2O equal to 1. But what happens? XH2O may not be 1. It can be less than 1. It cannot be more than 1. I will tell you a little. I will tell you. So, pH2O, partial pressure of H2O, is equal to XH2O into P total. Total is the lithostatic pressure and pH2O is the partial pressure. At XH2O equal to 1, the partial pressure of H2O is the same as the overload pressure. Have you understood? If pH2O is greater than P total, then you can imagine the pressure of the fluid is more than the pressure above it. So this will cause cracking of the overlying crust because nature does not tolerate this. So what happens is, if you have a fluid overpressure, then the rocks above it would crack to release the extra H2O. But there is no harm if pH2O, it has been reported, calculated from many terrains all over the world, especially high-grade terrains, where pH2O is less than P total. If that has to happen, then you can see here, XH2O will be less than 1. If pH2O is less than the P total, then XH2O necessarily should be less than 1. So what happens to this graph when XH2O decreases? This graph, you have to find out, but I will give you the clue. The graph, the reaction, the PT loci of the reaction, or the PT locus of the reaction, would shift to the left in a direction opposite to where this occurs, H2O occurs. So the fluid will move in a direction opposite to where H2O occurs. This is called from Le Chatelier's principle, which you studied in your school, or law of mass action, which you studied in your school. You please read it up. If you reduce XH2O value from the position of 1, the graph moves away from in a direction opposite to where fluid H2O occurs. So what happens is, this graph changes its position. So I am writing it. It's not correct, of course. That's it. This is a truth. XH2O, when you decrease it, or you can say it, the stability of the low temperature mineral. So if you decrease H2O, then what is happening? The stability of muscovite plus quartz is getting more restricted to the lower temperature. Have you understood? This is a truth for all metamorphic reactions. That if you reduce XH2O, then the stability field of the low pressure, low temperature assemblage shrinks to lower pressure and low temperature. In other words, this assemblage assemblage, K-feldspar plus aluminosilicate, this assemblage shifts to lower temperature, or making K-feldspar plus aluminosilicate more stable at lower temperature and lower pressure. This is an important point that will come into our discussion. Now, once again, I make myself a little clear so that we understand everything. We have muscovite plus quartz is equal to K-feldspar per aluminosilicate. So you have the fluid composition as H2O, and you can reduce XH2O, then the reaction curve moves to the lower temperature, lower pressure side. That means muscovite plus quartz becomes less stable for low H2O, but extends its stability to a high temperature if the rock is hydrous. So this is wet rocks and these are dry rocks. Wet rocks and dry rocks. So as you wet the rock, the stability field of the low temperature form increases towards higher temperature. And if you dry the rocks, the opposite happens. This is a well-known fact. Now, the same thing you could do if you might be wondering, Acha, if you have a fluid and you're reducing XH2O, fine, the curve moves this way. But say, for example, when XH2O is 0.2, what is there? What else is there? Because for a phase, you should have summation sigma xi, or you should have sigma xi equal to 1. So if your XH2O is 0.2, where is 0.8? What is 0.8? This is a discussion that we will do later on. Thermodynamically, it is not necessary to have anything else. Anyway, for the moment, we will not consider this because, if I go into that mold, then I will losing connect with my earlier lectures. I have only told you this because it's a thing that should be remembered in your mind. Because we'll come back to this several lectures later, and then you will find why I was saying this. So, here in this, if I write it this way, then in wet rocks, it will change. Now, I will give you a escape route so that you're not tormented. You're not tormented. I will give you an escape route. I will do this with a red pen. Let's say you have a binary fluid. Have you understood? You have a binary fluid. The fluid is this, and it is H2O, so that your original this thing Xi equal to 1, meaning XH2O fluid plus XCO2 fluid equal to 1. So that now you say, okay, I'm a little bit relaxed. There's nothing to relax. This is just because I want to help you out to understand it. So my fluid, when I say fluid, phase, then your sigma xi is equal to 1. That means XH2O plus XCO2 is equal to 1. Right? But remember, out of these two, only one is an independent variable. If you know XH2O, XCO2 is already fixed. Right? If you know XCO2, XH2O is fixed. So one variable is involved here. But if your fluid is pure H2O, like here, there is no XCO2. Right? No CO2. That's for sure. Right? So now, we go into a domain which requires a bit of understanding. Now, I take this, I will first assume this graph. That means XH2O is equal to 1. Have you understood? That means for the moment I am ignoring this. I am ignoring this because XH2 is equal to 1. CO2 has no role to play. Right? So now, if these are the formulae, excluding CO2 again, what are my system components? What are my system components? You can see here, my system components are K2O, Al2O3, SiO2, H2O. It could be written in some other way, but it doesn't matter. K2O, Al2O3, SiO2, H2O. 4 component system, where all the phases are there. And so here C is equal to 4. 1, 2, 3, 4. You see, I can write all formulas in terms of K2O, Al2O3, SiO2 and H2O. All formulas. So here C is equal to 4. What is P? You can see 1, 2, 3, 4, 5. Oh, 1, 1, 2, 3, 4, 5. 5. So phase 1, 2, 3, 4, 5. P is equal to 5. So F is equal to C minus P plus 2, which takes it to 4 minus 5 plus 2 is equal to 1. So muscovite quartz, K-feldspar aluminosilicate, we don't distinguish kyanite, sylvanite and andesite. We assume it's a phase. Aluminosilicate is a phase. Whatever that phase is. We'll talk about that later. So K-feldspar aluminosilicate fluid, all are phases. So you have 5 phases, 4 component system. So you have 1 valence. What does this mean? 1 is the valence. From other classes you must be knowing now, 1 variance means that one emitter, one input, one variable is not quantified. One variable is not quantified. If can do this, then the other variables can be quantified. Now I ask you, what are the other variables? What are the other variables? Is there any variable to do? Let's say what are the variables? You can see here pressure and temperature. These are the 2 variables of this line. Is there any other variable? Say for example XH2O. What is the variable? But the value is already quantified, isn't it? We have taken pure H2O. So the variable is already quantified. So that XH2O is not a variable. Not a variable. What are the other things? The other things are all pure phases. So all of their activities, phase component activities are unity. Unity, all are pure phases. Also fluids. As we have taken it along curve 1. All are fluids. So, C equal to 4, P is equal to 5, F is equal to 1. Which means that if you assign a particular pressure value, one of the unknowns, if you assign, that means you write P is equal to 5 kilobars. P is equal to 5 kilobars. That means P is equal to 5 kilobars an equation. You know, number of variables minus number of equations is equal to, variance is equal to number of variables minus number of equations. That is what is variance. How many, it gives you how many variables are unquantified. So if you add P is equal to 5, then adding one equation yourself. So you're adding to the equation. So variable minus equation now becomes 0. That is no variance. That means if you take this value P at this curve XH2O, this is your T. So if T is fixed. That is what Gibbs phase rule says for this curve. Muscovite plus aluminosilicate plus H2O. You say that I take a pressure value, so P is equal to something. You add an equation at the end, and therefore variable minus equation now becomes equal. So variance becomes 0. Of course variance becomes 0 because now you can directly find out temperature. Right? Similarly, you can go the other way. You can take the temperature and it intersects this curve here, and then you get the pressure value. I hope you have understood it. I hope you have understood it. Now comes the more difficult part, and that's the suspense. Now, have a look. If I take my fluid on the binary system, now what happens? In the binary system, my fluid. Now, instead of this, you also need CO2. Yes or no? Because the system component has to describe this composition. Unless you have CO2, you cannot write for CO2 because CO2 does not occur anywhere else. So now what you have done is, you have increased this one to 5. Right? Increased this thing to 5. But P, same. 1, 2, 3, 4, 5. 5. So 5 remains 5. So now we start 5 minus 5 plus 2. There you go, 2. What is this 2 now? Gibbs phase rule tells you that if you want to quantitatively characterize your equilibrium, then you need to give me 2 variables. 2 variables you need to give me external to the system, and I will give you the rest of it. Now, what are the variables? What are the variables? For muscovite, quartz, K-feldspar, aluminosilicate, no change. They are no solid solution. They are all pure phases. So the variables now are pressure, temperature, and now XH2O is a variable. Do you see that? Now your XH2O is a variable. Gibbs phase rule tells you your variance is 2. And your variables are pressure, temperature, XH2O. That means if you give either of these 3, either 2 of the 3, the other can be quantified. Either 2 of the 3 and the third one will be quantified. So out of the 3, there are only 3 variables possible here. Out of this 3, Gibbs phase rule says if you can quantify 2, any two, I give you the third. The third can be computed. What is it like? Now we go back to this diagram. You see here, look here. What is there? XH2O equal to 1 is off. It's out of the question now. But all values other than 1 and less than 1, all values are applicable. So so this is the pressure value. You have assigned P is equal to, so in the equation, number of variables minus number of, what is variance is equal to number of variables minus number of equations. So now I have added P is equal to something. So the variance was 2. Now when I add P is equal to 10, I reduce one equation because I've given you one equation. Now the variance becomes 1. Now if I tell, so that means if at this pressure, if you have this XH2O, this XH2O, this XH2O and this XH2O, they will give you different temperatures. Have you understood? So, you have to know which curve represents your equilibrium. That means you should know the XH2O value of your system. Right? That means if XH2O is equal to 0.2, then this is the temperature. If XH2O is 0.4, this is the, remember, this is the pressure, right? This is the pressure. So, if you have XH2O, then you get different temperature. Different temperatures. If you have different XH2 value, you have to assign which value XH2 you have. Or, so, if you can assign an XH2 value, then you know your temperature. You assign the P value. One equation. You have assigned this is actually a new lecture because my storage of my camera got exhausted. So I did this last evening, but it was not recorded, so I'm recording it again. It might sound a little incoherent, but then I think I will be on track. Yeah, right. So continue. What happened is, so in the last lecture that we were talking about, we said that we can put in a value of pressure, and if this, say for example, if this is the pressure value, and I draw vertical lines, these vertical lines, you see this pressure value, at this pressure value, the muscovite plus quartz is equal to K Fels per aluminosilicate fluid valve, this one, is intersected at several points, 1, 2, 3, 4, 5, and so on. Now, say for example, when I take the pressure value P, then it intersects it, and therefore I still don't get an estimate of whether XH2O, what is the values of XH2O and temperature. So what is important is, I have to assign, say for example, an XH2O value. So if I assign an XH2O value, says 0.2, then this is the temperature. Pressure and XH2O value, then this is the temperature. If same pressure at XH2.4, this is the temperature. Similarly, as I change the XH2O value, the temperature values change. Right? So, according to the Gibbs phase rule, the variance is 2. That means we have to add 2 inputs. 2 input means pressure is equal to something, XH2O is equal to something. So now this I don't have in the system. The system doesn't get it for you. These are inputs from outside, and once you do the inputs, Gibbs free energy says the system can be characterized, but does not say, numerically all variables are characterized, but does not say what are the variables. But we know that the variables are pressure, temperature, and XH2O. So when you get XH2O value and pressure value, you get a temperature value as your output. Right? Now, now you can change this all over. Say, for example, you don't know the XH2 value, but you know the pressure temperature value somehow from from other sources. You know the pressure temperature value, but you don't know the XH2 value. So what happens? So you take this pressure value, say this equation, so P is equal to something, and then you take, say for example, this temperature, and this temperature is here, right? So the pressure and the temperature which you bring in from outside, which are essentially inputs, your output is the value of XH2O. So if you know the pressure and temperature, the XH2O value turns out to be 0.4. So that is it. The variance tells you the number of input variables that you need to be, or you need to quantify from other sources, and if you do that, the system, all other variables in the system can be quantified. Here, for example, is a case where XH2O then will become quantified if you know pressure temperature. So we know that there are three variables, pressure, temperature, XH2O, and any two of them would give you the third. But this is where H2O CO2 is a binary mixture. Now, these were the two pens that I used. The black pen here was used where XH2O was pure. The red pen was used when fluid was H2O CO2 mixture, sigma xi equal to 1, XH2O plus CO2 equal to 1. That is when I use this red. And now I'm going to use this blue. Right? I'm going to use this blue. And you can ask me, why do you want to use the blue now? See here. I only introduce CO2 so that your miseries are reduced. But now I want to go into a field where you will find that there is a great logic. There is a logic, and a problem can be overcome. Now first we'll tell what is the problem here. Now you see, in this assemblage, muscovite, quartz, feldspar, aluminosilicate, we know that muscovite has an OH2 radical. So H2O is held as structural water in the assemblage, in muscovite in this assemblage. Right? There is therefore evidence that the fluid contained H2O. But there is no evidence in this assemblage that CO2 was also a part of the fluid. There is no evidence whatsoever. So I introduced this so that it would make things life easier for you. But basically, there is no logic why I should use CO2. Why not CO? Why not CH4? Why not something else? Because I don't have evidence. So what happens? This that I introduced was something like a fictive thing to keep your mind, okay, I understand. But now we have to go into a domain where I don't want CO2 anymore. Because why? I don't have any evidence for a CO2 containing fluid. So what do you do about it? That's the catch. And for that, I will give you an idea. Say, for example, you have a silica saturated rock. Say, for example, granite. In granite, if some of you have seen thin section, you can see that there is quartz grain under the microscope. Even mesoscopically in the field, you can see that there are quartz grains. That is a quartz saturated rock. And if you have a mineral present, then activity of SiO2 in quartz, SiO2 is the component, quartz is the phase. This I told you before. Should be equal to 1. Activity of a pure phase should be equal to 1. So if the mineral is present, if the mineral is present, then activity is equal to 1. Now you know activity is equal to mole fraction. Let's approximate activity is equal to mole fraction. We will talk about that much a little later. But for the moment, activity is equal to H2. That means X SiO2 quartz is equal to 1. If quartz is present. What happens if quartz is absent? Quartz is absent. Then activity of SiO2 in quartz is not equal to 1. It is less than 1. Those rocks are called silica undersaturated rock, like an ultramafic rock or a peridotite, a ledsolite. These are all ultramafic rocks. Or even, for example, basalts or gabbros. You don't get quartz normally. You normally don't get quartz. So what happens is, quartz is absent and activity of SiO2 of quartz is therefore less than 1. What value we don't know. The lower the value, the greater is undersaturation. That we can understand. But the quantified value we normally don't know. There are ways to know, but that's different. Now, if we use this idea, mineral present, mineral absent. Mineral present, sigma xi is equal to 1. That means, say for example here, we can therefore consider, we can have a fluid which say does not exist as a phase. But the fluid exists, but not as a phase. Not as a phase means sigma xi in the fluid is equal to 1. Have you understood? In this case, H2O, if that's the only phase component, is less than 1. This is a situation where fluid does not exist. It does not mean that the fluid is not there. It means fluid is absent as a phase. It does not mean that there is no fluid. There is fluid. But the sigma xi, the total mole fraction of X component in the fluid, is less than 1. As opposed to this one, sigma xi equal to 1, where a fluid phase is present. So you see, that is why I introduced CO2, so that you can consider fluid as a phase. But if we consider that, okay, there can be a situation where fluid does not exist as a phase, but there is a fluid. So this is called a fluid absent situation. And we know that H2O was there, definitely. So it was a hydrous fluid, but fluid did not exist as a phase. So now, if we do this, and if we still want to persist with this diagram, and we had a variance of 2 by introducing CO2 somehow forcefully without having any evidence, if we say, I don't have CO2, so I cross this over. I don't have CO2. But I want to have a very similar situation. So if I have to do this, then the variance has to be 2. The variance has to be 2. Have you understood? Then what are the variables? Now, what are the variables? You see, it was written XH2 is equal to 1 minus CO2. Now the variables are pressure, temperature, XH2O. I am not saying 1 minus XCO2. No, I am not saying. Not within bracket 1 minus XCO2. Why? Because there may be no CO2 there. It's just a hydrous fluid, but the fluid does not exist as a phase. That means sigma xr is less than 1. It cannot be 1. If your equilibrium is on this curve only, then XH2O is equal to 1. And if you do that, then sigma xi equal to 1. This is for fluid present situation. Fluid absent, all the left part. So now our variables are pressure, temperature, and XH2O. And let's say we have a variance of 2, same as carbon dioxide with carbon dioxide theory, but there is no carbon dioxide. So what will happen? Now you see, for such a system, it will be, the system component will be 1, 2, 3, 4. Not 5, because there is no CO2 to start with. Okay? So you have 1, 2, 3, 4. So your F value is equal to 4. Components are 4, not 5, which you did by adding CO2. Not necessary here. And pressure temperature is plus 2. So if you have to have a variance of 2, so that I preserve this diagram, then the number of phases should be 4. That's crucial. Then you have a variance 2. Why 4 phases? Why 4 phases? Why not, like here, 5 phases? Because phases are 1, 2, 3, 4. Not fluids. Because fluid is not a phase anymore. Fluid is not a phase. Phase means this. No phase means this. So here, the number of phases are 4, not 5. Like we did here. Like we did here. Why? Because fluid is present as a phase. Here, fluid is not present as a phase. So then, we go back to this situation, where degree of freedom, or the number of input variables, or the unquantified variables in the system contains 1, 2, 3 variables. Now, Gibbs phase rule says that if there is 2 values that are input, then the third can be found out. So here we have 4 phases. So now you can see we are back again to the same situation. So I draw the blue line. Right? So I take a p value. That means I have introduced an equation. P is equal to 5 kilobar. I've introduced an equation. You remember again, variance from your side, variance is equal to number of variables minus number of equations. Okay? So if your variance is 2, as here, then the number of equations, number of variables is 1 more than the number of, 2 more than the number of equations, naturally in the system. But we add p is equal to 5, so we have added an equation. Variance from 2 drops to 1. Have you understood? If we add another equation, then the variance drops to 0. So you don't need anything else to do it. So again, if I take a particular pressure value, and say, for example, I take a particular temperature value, say here. This is the temperature value and this is the pressure value. Then you see, you will always have a curve passing through this, say 0.7. Have you understood? 0.7. So at this pressure, which you have input from outside, at this temperature you have put in from outside, then XH2O can be retrieved. And again, if we take a particular value of pressure, in other case, if T is unknown, then you have to have XH2O known. So you see, at this particular pressure value, these are the temperatures possible over this range. Have you understood? So these are the temperature. So if you can define your XH2O value as 0.2, then this is the temperature. If your value is 0.4, this is the temperature. So that's all it goes. But what is the advantage of this blue thing? The advantage is I am not unnecessarily, really unnecessarily evoking CO2. I am dealing with what I see and not with what I don't see. That is the advantage of using fluid present and fluid absent situation. Remember, fluid present is summation mole fraction is equal to 1. Fluid absent means sum of the mole fraction not equal to 1. It's a big difference. We will see that later. It's a huge difference because when you say that x1 plus x2 plus x3 plus x4 is equal to 1, it means it's an equation. Okay, it's an equation. It's a tug of war between variables and equations. So it's an equation. But if you write x1 plus x2 plus x3 is not equal to 1, that's not an equation. You lose one equation. Losing an equation, one equation, means a huge thing in metamorphic petrology. Right? So this is what is important here. We talked of first with the first black lines, fluid phase completely filled with XH2O. This line. Then we talked mix the fluid. We called it a mixed fluid equilibrium where you have H2O, CO2. And then we discussed it. Variance is 2. And then with the blue line, this represents where fluid is not a phase. It's not a phase. That means it's a fluid, phase is absent. It's a fluid absent situation where the theoretical reason for that is sigma xi. Fluid sigma xi of the fluid. Sigma xi of the fluid is not equal to 1. Sigma xi of the fluid is not equal to 1. Sigma xi fluid is equal to 1. Sorry, I wrote it equal to 1. It's not. Sigma xi is less than 1. Addition of mole fraction should equal to 1. If it not, then it's a fluid absent situation. The phase must be absent. Just like in your silica saturated rock, activity of SiO2 equal to 1 means the rock should show quartz. If it does not show quartz absent, then activity of SiO2 in quartz is less than 1. It's not 0. It's less than 1. That is the most important thing. So when you go through it, I think you should go through it 2 times because I wrote here is equal to 1. It's not equal to 1. It's less than 1. Right? So you make that correction when you're going through it second time. So this is where I end my talk here. In the middle it looked a little jumpy, but that is because of a technical problem here. But okay, so now if you have any questions, you please let me know through the Google Classroom, or if you write me a private email. I have given you my email ID before, so if you write through, I will still post it to the Google Classroom for others to see. Okay, and I will not try to put your name, so I will, if possible, I will not try to put your name. I will just put the question, but try to get it yourself first. Normally, it's very logical. Normally, it's very, very logical. Remember, fluid absent means sigma xi less than 1, not equal to 1. And fluid present means sigma xi equal to 1. Right? Thank you. And when you read these last 3 lectures, you read it in the sequence 3, 4, 5, not 5, 4, 3. You will be lost. Read in the sequence 3, 4, 5 and give it several reads, because it's very important to conceptualize the ideas in metamorphic petrology. I can derive a lot of equations and I can fill up the board and show off, but I never do it. I try to get it try to understand the philosophy of it. Everything else will fall in place once you've understood the philosophy. Okay, thank you. And we need to start with our metamorphic petrol laboratory class.